Assalamu alaikum class. Here we are going to discuss the second topic of chapter number 3, and we have started chapter 3 in the previous lectures, vector differentiation, and we discussed at how we can take the derivative of any vector. And now in this lecture we are going to discuss about the partial derivatives of the vectors. We all know that the partial derivatives are defined when we are having a function depending on more than one variable. Similarly, if a vector is depending on more than one variables, then we introduce the concept of partial derivatives at that point. So let A be a vector depending on more than one variables x, y, and z. And clearly these variables are scalars, not the vectors, and the vector is represented by a of a x, y, z. As previously we discussed that the vector was depending on only one variable u, and now we are talking about the vector depending on three variables x, y, and z. Its partial derivatives with respect to x is defined as partial a over partial x, limit delta x approaches to 0, a of x plus delta x y z minus a of x y z over delta x. So here you can see that we are just changing x, the other variables are taking to be constant, and we have used the same definition we introduced for the derivative. So when we talk about the partial derivatives, we apply the rules of differentiation with respect to that one variable, and the other variables are remains constant. So this is the same way as we defined for the scalar functions. The partial derivative with respect to y is defined over here, and we are changing y only, and here is a partial derivative with respect to z. In previous lectures we also discussed about the continuity of a function. So if we are defining a function depending on more than one variables, it means we may be able to define the continuity of such functions as well. So for a scalar function phi of x y, depending on the two variables x and y, it's said to be continuous if its limiting value is equal to the functional value, that is limit delta x approaches to 0, delta y approaches to 0, phi of x plus delta x, y plus delta y is equal to phi of x y. So this is representing that we are changing the variable with a very small amount, and the functional value is equal to the limiting value. So we also discussed the continuity with respect to the epsilon delta condition. So here we have the epsilon delta condition as well. Phi of x plus delta x, y of y plus delta y minus phi of x y is less than epsilon whenever delta x mod is less than delta and delta y mod is less than delta. So here you can we have discussed previously as well that these epsilon and delta are very small positive numbers. So this is representing that whenever the change in x and change in y are very small, the limiting value, the difference between limiting value and functional value are also very small. So such function is representing the continuity at the point x and y. So similarly it can be defined for vector functions as well depending on more than one variable. So we just have to introduce the concept that we are defining a vector function over here, and the other definitions remains the same. Clearly, a function is said to be differentiable if its first derivative exists, and for functions depending on more than one variable, these are also said to be differentiable if they have continuous first partial derivatives or the first order partial derivatives. We can also define the higher order partial derivatives as well, like partial square a over partial x square, that is the double derivative. So with respect to x, here we have partial square over partial x partial y. Here you can see that we are introducing the two derivatives. So at first we have to take the derivative with respect to y and then with respect to x. But in case of partial derivatives, the order doesn't matter anymore, because partial square y over partial x y is equal to partial square a over partial y partial x. So the order doesn't matter, that either you take the derivative with respect to y and then with respect to x, or you take the derivative with respect to x first and then with respect to y. So here we have an example as well. Let's suppose f of x y is equal to x cube y square plus 2x minus 5xy. So it's a double derivative with respect to y and then with respect to x is going to be, when we take the derivative with respect to y, x cube will act as a constant term and the derivative of y square is 2y. Then the derivative of constant will be 0 as x is representing as a constant over here, and now 5x will be the constant and the derivative of y is 1. So here we have 2x cube y minus 5x, and now we have to take the derivative with respect to x. Now y will act as a constant term, so 2y is constant, the derivative of x cube is 3x square, so we will have 6x square y minus 5 is the answer. And if I interchange the order, that I take the derivative with respect to x first and then with respect to y, what will happen if I'm going to take the derivative with respect to x first? So y square will be the constant term, So the derivative of cube is 3x square into y square. Derivative of 2x will be 2, and the derivative of 5x will be 5, and the y will be act as a constant term over here. And now I'm going to take the derivative of this one with respect to y. So the derivative of y square is 2y, so I will have a 6x square y. The constant term derivative going to be 0, and the derivative of minus 5y will be equal to minus 5. So you can see that the both derivatives are the same. Although both derivatives are the same, that is, the order doesn't matter in such cases or in partial derivatives, but this is really doesn't mean that if you have written partial square f over partial x partial y, it means that you can take the derivative with respect to x first. Geometrically, it represents that you have to take the derivative with respect to y and then with respect to x. So it means that I can replace this expression with this expression, but when I am going to solve the expressions, I have to take the derivative with respect to y first and then with respect to x, and in this case I have to take the derivative with respect to x first and then with respect to y. So although the order doesn't matter, but when we are solving the question, the order is really very important. Next, we have some rules for partial differentiation. These are the same as we discussed previously for the derivatives. So here we have the partial derivative with respect to x of a dot b. So we have discussed first that we have take the derivative of the vectors one by one. So a dot partial b over partial x plus partial a over partial x dot b. So if I take the derivative of a cross b, it means the same rule, a cross derivative of b plus derivative of a, or partial derivative of a with respect to y cross b. And if we have the double derivative, partial square y over partial square over partial y partial x of a dot b, so again we have to apply the rule of dot product we have discussed over here. So what will happen, I have to take the derivative with respect to x first and then with respect to y. So I have to apply the product rule over here, a dot partial b over partial x plus partial a over partial x dot b, and now I'm going to take the derivative with respect to y. So I have to apply the product rule on this first and then I will apply the rule on it, this one as well. So this is going to be a dot partial square b over partial y partial x plus partial a over partial y dot partial b over partial x plus, now I'm going to apply the rule on it as well. So I have to take the derivative of b first, so partial a over partial x dot partial b over partial y plus partial square a over partial y partial x dot b. So this is how we can perform the double derivative as well. Before solving the questions or before applying the concept, we have one more definition over here, differentials of vectors. So we also know that differential is simple df, it represents a small change. So there is a basic difference between the derivative and differential, that when we talk about the derivative, it means we are talking about the change in the function with respect to some variable, but when we talk about the differential, it means we are just talking about the small change in the function, not with respect to some variable. So here we have some rules of differentials. So differential of vectors follow the same rules as it defines in calculus, that is for the scalar functions. If a is a vector with components a1 a2 and a3, so its differential is simply da1 I cap plus da2 j cap plus da3 a cap. So the variable doesn't matter over here, that with respect to what variable we are defining the changes, because differential is talking about the change only, a small change. So differential of a dot b is equal to a dot differential of b plus differential of a dot b. So the rules are the same. And here you can see that the differential, if you're talking about the function depending on more than one variables, differential is defined as partial over partial x dx plus partial over partial y dy plus partial over partial z dz. So here we are having an example as well. Let f of x is equal to x cube plus 5x square. So its derivative, we know that if we take the derivative with respect to x, it is going to be 3x square plus 10x. And if we talk about the differential, so df is going to be the differential of x cube will be 3x square dx, and differential of 5x square will be 10x dx. So here is the basic example of differential. Here we have question number 15. If a vector A is given to us and we have to find out some partial derivatives defined over here. So at first we are going to find out the partial derivative with respect to x. It means we will take the partial derivative of I component, then partial derivative of j component, and then partial derivative of k component. So its partial derivative with respect to x is going to be 4xy minus 4x cube I cap. Then its derivative with respect to x is going to be exy, and then we have to take the derivative of the power, and the partial derivative of xy with respect to x is obviously y. Then we have minus y, and the derivative of sin x is cos x, so minus cos x j cap, plus the derivative with respect to x is going to be 2x cos y unit vector k. Then we have to take the partial derivative with respect to y. It means when we take the derivative with respect to y, x will act as a constant term. So here x is a constant one, so its derivative with respect to y is going to be 2x square. This one will be 0, so 2x square I cap. And when we apply the differential or the derivative on e power xy, it is going to be e power xy, and the derivative of xy with respect to y is x. Then derivative of y is 1, so sin x will act as a constant over here, so minus sin x, and its derivative is minus x square sin y. Then we have the double derivative with respect to as partial square over partial x square. It means we have to take the double derivative with respect to x. So here we have partially over partial x we have defined. So again we have to take the derivative of this expression with respect to x. So this is going to be 4y minus 12x square I cap, and this is going to be e power xy into y, and y already was here, so it is going to be y square e power xy plus y. The derivative of cos x is minus sin, that's why we are having plus y sin x, and the derivative of 2x is going to be 2, and cos y will act as a constant coefficient, so it will remain the same. Then we have partial square a over partial y square. It means we have find out the partial over partial y, and then we have to take its derivative with respect to y again. So here we have partial square a over partial y square, and then similarly you can find out the other factors as well. Next we have question number 16. If phi of xy, a scalar function, is given and the vector function a is also given, and you have to find out partial cube over partial x square partial z phi of a at the point 2, -1 and 1. So at first we will find out phi a, that is we will multiply this scalar function with each component of the vector. So here we have multiplied over here, and then we are going to find out this expression first, that is we have to take the derivative with respect to z first, and then the double derivative with respect to x. So how we can solve it? So the derivative with respect to z is defined over here, and then we are going to take the derivative of the answer with respect to x and again with respect to x. So here is the final answer, and now you are going to put the point 2, -1 and 1, that is x is equal to 2, y is equal to -1, and z is equal to 1. So inserting the values over here, we get the answer to be 4i cap minus 2j cap. And now the question number 17 that you have to solve on your own. Thank you.